we've already seen that there are 5 addressing modes. We've already looked at the addressing modes. So now we're going to look at different instructions from those addressing modes. So first instruction that we are taking here is, first instruction that we are looking is MVIA, comma data. So we've seen that this is instruction of immediate addressing mode. This is immediate addressing. So this is going to be a 2-byte instruction. 2-byte instruction. 1 byte is taken by the opcode. 1 byte is taken by the data. This is going to be a 8-bit data. So this is a 2-byte instruction, and it is going to take 2 machine cycles. I guess we've taken up the timing diagram for this instruction. This is going to take 2 machine cycles. One machine cycle is going to be opcode fetch 4 T states, and one machine cycle is going to be memory read to just extract the data. This is going to take 3 T states. So this is going to be a 7 T states long instruction, 2 machine cycles, 2 byte is the size of the instruction, and this is going to be immediate addressing mode. What is this instruction going to do is, this is going to load the accumulator with given data. Load accumulator with given data. And where is this data going to be located? It is going to be located in the next memory location, next immediate memory location. Okay, so what we can do is, we can just look at all the instructions of immediate addressing mode first. Then we can look at instructions from other addressing modes. I think that would be better. So arithmetic operations in immediate addressing mode are going to be, to add a data, you're going to use an instruction ADI, comma data. So what this instruction is going to do is, this is going to add the data given in the instruction add immediate. What does this mean is, add immediate. What happens in add immediate is, you're going to give a 8-bit data in this instruction, 8-bit data, and what happens is, contents of accumulator are added with the data, and the final result is going to be stored in the accumulator itself. So this is also a 2-byte instruction. This is going to be a 2-byte instruction, and to perform it, we're going to need 2 machine cycles. Machine cycles, one opcode fetch, and then next is going to be memory read to get the data. So this is going to take up 2 machine cycles, and size is going to be 2 bytes. And what operation it is doing is, it is adding the given data, this data, to accumulator, and the final result is going to be stored in the accumulator itself. Now, next instruction that we're going to look at is ACI, 8-bit data. Okay, everywhere where you're giving data, this is going to be 8-bit data. In 8085 we're using 8-bit data. Okay, data bus is 8 bits only. Also we know that every memory location is storing 8 bits of data. So what does this instruction do is, this is going to add the data along with the carry. What does this instruction stand for? Add with carry immediate. So this is going to add the contents of accumulator with the data along with the carry and store the result in the accumulator itself. Fine. So this is also a 2-byte instruction, and it's having 2 machine cycles, opcode fetch and memory read, right? Fine. Next instruction that we are going to look is SUI. SUI is subtract immediate. So what happens is, the given data is going to be subtracted from the contents of accumulator, and the final result is going to be stored in the accumulator itself. This is also a 2-byte instruction and having 2 machine cycles. Okay, so all these are going to be 7 T states. Okay, just write. This is going to take up 7 T states. This is also going to take up 7 T states. Right. Next instruction is going to be SBI. SBI. So what happens in this is given data is going to be subtracted from A along with the carry or borrow according to the status of carry flag. If this is 1, then 1 is also going to be subtracted, otherwise 0. Fine. So here data is going to be subtracted along with borrow. Okay. This is also a 2 byte long instruction having 2 machine cycles. And it's going to take 7 T states. So this is, okay, just look at all the instructions one more. This is move immediate. So what happens is whatever data you're giving in the instruction, it is going to be stored in the immediate memory location, and it will be moved to the accumulator. Then we have ADI data, which is add immediate. The data that you're given in the instruction is going to be added to the accumulator, and final result is going to be stored in the accumulator itself. Then we have ACI, which is add with carry. Here carry is also taken into consideration. Then you have SUI, which is subtract immediate. Only data is going to be subtracted from accumulator and result is going to be stored in the accumulator. Then we have SBI, which is subtract with borrow immediate. Here along with the borrow or carry, data is going to be subtracted from accumulator and the result is going to be stored in the accumulator itself. All these are 2 byte long instructions and having 7 T states, 2 machine cycles, one for opcode fetch and second for reading the data memory read. Right. Next instruction that we can look here is, next instruction is ANI, and immediate. So what is this going to do is, this is a logical operation, or the operations, see here we looked at 4 arithmetic operation: addition, add with carry, subtraction, subtract with borrow. These were 4 arithmetic operations that we had in immediate addressing mode. Now we are looking at logical operations. So AND is the first logical operation that we are looking. So what will this do is A and 8-bit data. So all the logical operations in 8085, all the logical operations that we are looking in 8085 are bitwise logical operation. Bitwise means every single bit, every LSB of accumulator and this data, and every MSB of accumulator and this data are going to be AND separately. Okay, so these are going to perform bitwise operations. So ANI is going to this is AND immediate. So this is going to perform AND operation between accumulator and the given 8-byte data. Again 2 byte long instruction, 2 machine cycles, opcode fetch and memory read, and 7 T states. So this is a first logical operation that we are looking at. Next operation would be ORI. ORI is or immediate. So what happens here is, contents of accumulator will be odd with the 8-bit data. Size is 2 bytes. Right. So this is going to be AND operation, this is going to be OR operation. Next we have XOR operation, XOR. So you already know all these are going to be bitwise operations. So here all the instructions in this immediate addressing mode, mostly they are going to be 2 bytes and 2 machine cycles. Especially all the instructions on 8-bit registers are going to be 2 bytes and 2 machine cycles, only 7 T states. We have several instructions on 16-bit, that is we have several instruction register pairs. So they can be maybe 3 bytes long or taking more T states. 8-bit registers, all the instructions are going to be 2 bytes and they will take up 7 T states, 2 machine cycles. Fine. So next instruction that we've got here is CPI. CPI is compare immediate. Compare. Okay, so what is this instruction going to do is, see, what happens in this instruction is, this is actually like subtract only, but here result is not going to be stored. We are just comparing that whether this data is bigger or whether the contents of accumulator are bigger. We are not subtracting, we are just comparing. So what happens is this data is going to be subtracted from the accumulator, and based on the status of carry flag we are going to judge whether this A, contents of A are bigger or the given data is bigger. A is compared with data. So actually A minus data is going to be performed. If zero flag is 1, means that data and A both were equal. So this is we conclude that they are equal. But if zero flag is 0, and carry flag is 0, means borrow, which is, see, we are performing subtract operation, right? So this is borrow. Borrow flag is 0, that means A is greater than data. And if zero flag was 0, which means that result was not 0, and carry flag is 1, that means we had to take a borrow. This means A was less than data. So this is what this instruction is going to do. This is also a 2-byte long instruction, 2 machine cycles and 7 T states. Fine. So this is what CPI is going to do. So these are all the 8-bit instructions that we had that were operating in 8-bit. Now we have several instructions that are operating on register pairs. Okay, they are going to see, we have several register pairs in 8085. Fine. So we know that we have a accumulator, we have register A, then we have register B and C. Both of them combinedly are making a register pair BC. Similarly, D and E make a register pair. H and L make a register pair. We have also learned about PSW, program status word. So A and PSW also make a register pair. We can perform several operations on them. Okay, so we'll see how we are performing operations on them, but for now mostly we are using these BC, DE and HL pairs. So we have several instructions that are going to be performed on register pairs and not on a single register itself. So one of them that we are using in immediate addressing mode is LXI RP 16-bit data. For example, I'm giving an instruction LXIB, 2070. So what is going to happen is this is a register pair we are seeing, right? Each register is 8-bit. Each register has a size of 8-bit. So a register pair is going to be 16 bits long, right? So here we are giving 16-bit data which is going to be stored in B and C registers. So how is this going to be stored? Higher bits of the data, upper bits of the data in upper register, lower bits of the data in lower register. This is how storing is going to take place. What does this instruction do is load immediate register pair. Load immediate means in the next memory location, whatever is the data, just store it, load it in this register pair. So what happens here is whatever data you have given in the instruction 2070 is to be loaded into BC register pair. And how is this loading going to take place? Upper bits of the data in upper register, lower bits of the data in lower register. This is how this is going to take place. Okay, this is how LXI is going to work. Fine. So this is a see, we have looked at instructions like this, right? MVI B, 20, MVI C, 70. So these two instructions combinedly also were doing the same thing, right? Where we were doing the same operations using these two instructions. This instruction took 2 bytes. This instruction took 2 bytes. This LXI RP, this complete instruction is taking 3 bytes, going to take 3 bytes. See, 1 byte for the opcode, 1 byte. 2 bytes for the data. So this is going to take 3 bytes completely, right? So we have saved up 1 byte of memory using this instruction instead of these two. Also, how many machine cycles is going to take? This is going to take 3 machine cycles. 3 machine cycles. I think you can guess also. One machine cycle is going to be opcode fetch, of course. Then we are going to have 2 memory read cycles. To read 16-bit data, you're going to require 2 memory read cycles, which sums up to 3 machine cycles and 10 T states. Whereas using these two instructions, we needed 14 T states. 14 T states, right? So we are saving up some time and some memory using the single instruction instead of these two instructions. Okay? But just one thing that you need to remember is higher byte and higher register. Okay, this is the only thing. Okay, so now we are going to look at some instructions from direct addressing mode. So we had a look at instructions from immediate addressing mode. Now we're going to look at instructions from direct addressing mode. Fine. So what happens in direct addressing mode is we are giving the memory location, the address of the memory where data is located directly in the instruction. You just have to reach that memory location, extract data and load. Fine. So first instruction that we're looking in direct addressing mode is LDA 16-bit address. LDA 16-bit address. So what it is going to do is it is going to load the accumulator with the data located at the memory location pointed by the 16-bit address. A is going to be loaded with contents of 16-bit address given in the instruction itself. Okay, load accumulator with the data in 16-bit address. So size for this instruction is going to be 3 bytes. 1 byte is going to be opcode and 2 bytes is going to be this 16-bit address. So this is going to be a 3 bytes long instruction and having 3 machine cycles which are opcode fetch and 2 memory read cycles to read the data. Okay, I'm really sorry. This is going to have 4 machine cycles, 1 opcode fetch, 2 memory read cycles to read the address, and then 1 more memory read cycle to read the data from this address. So this is going to have 4 machine cycles. This is going to be 4 T states, 3, 3, 3. So this is going to have 13 T states. 4 machine cycles, 1 opcode fetch and 3 memory read cycles. So this is going to load the accumulator with the data located at the 16-bit memory location given in the instruction. Next instruction that we are looking at in direct addressing mode is STA 16-bit address. So with the help of this instruction, we were loading some data into the accumulator. With the help of this instruction, we are loading the data of the accumulator into memory. Store accumulator means we are storing the content of the accumulator in some memory location. So this is what this is going to do is this is going to load, better say store contents of accumulator, at specified memory location. At specified memory location. So this is doing memory writing. We are doing memory writing here. We're doing sort of memory writing here. So this is also going to be a 3 bytes long instruction. This is also going to have 4 machine cycles. Opcode fetch, memory read. Opcode fetch for just fetching the opcode, 2 memory read cycles to read the data, and then 1 memory write cycle. So this is also going to take up 13 T states. Fine. So next instruction that we are looking here is load HL direct LHLD 16-bit address. So here just instead of accumulator, HL pair is going to be loaded. Okay, so this is load HL direct. So what we are going to do is, whatever address you are giving here, you are going to go at that address and load HL pair with that address. Suppose we are taking an example. LHLD 2008. So what happens is you are going to go at memory location. Suppose this is a memory. Suppose this is memory location 2008, this is 2009, this had some data 1A, this has 2C. So what happens in HL pair, we are going to load this data, okay, and one rule I have already told you, less memory location in lower register. Okay, so contents of 2008 going to be loaded in L, contents of 2009 in H. So this is going to be, contents of H are going to be 2C, contents of L are going to be 1A. This is how they are storing data. They are storing data located at this memory location into HL pair. Fine. So similarly, this is going to be a 3 bytes long instruction. 3 bytes, 1 for opcode, 2 bytes for the address. And machine cycles are going to be 1 opcode fetch cycle, 2 memory read cycle for this address, and then again 2 memory read cycles for the data. So these are going to be a total of 16 T states and 5 machine cycles. Okay, so what is this going to do? This is going to load HL directly for the data from the given memory locations, memory addresses. Next is going to be store HL direct, SHLD, store HL direct. So here we were just reading data from memory and storing in HL pair. Now what we are going to do is we are going to store the contents of HL pair into the memory, into the given address. Fine. So this is just opposite of this. We are going to see an example here also. Suppose you have and contents of HL pair was, suppose these were the contents. So how they are going to be stored in memory, we are going to see. So this lower register is going to store its data into the lower address. So 3-4 is going to get stored here, and 1-2 is going to get stored here. This is how storing is done. This is how memory write is going to take place. So similarly, this is a 3 byte long instruction. It is having 5 machine cycles, which are opcode fetch, memory read, and 2 memory write cycles. 2 memory write cycles to just write this data. Fine. So for now we're just having these much instructions in direct addressing mode. We're not having a lot of instructions in this addressing mode since it takes up a lot of memory. Other than these, if we find some instruction, we are going to look at them separately in miscellaneous instructions. So next we are going to look at indirect addressing mode. Indirect addressing mode. What happens in indirect addressing mode is we are not giving the memory location directly in the instruction. Also, memory location is not the next immediate memory location. We have to extract the location of the memory from somewhere in the microprocessor, most probably from HL pair. HL contents of HL pair are going to point the memory location. Okay, and from that memory location we are going to extract the data. So this is what is happening in indirect addressing mode. First instruction that we are going to see here is MOV A, M. MOV A, M, which means move to the accumulator contents of the memory. Move to the accumulator contents of the memory. So this is the destination. Accumulator is the destination. Memory is the source. Memory is the source. Copying takes place. Okay, copying is going to take place. But where do you get this memory location from? Where do you get the address of the memory? So A is going to be loaded with the memory, loaded with the contents of the memory, address of which is going to be pointed by HL pair. This HL pair is going to have some contents, something is going to be stored in this HL pair. Wherever this HL pair indicates, whatever address this HL pair tells, contents of that memory location are going to be stored in A. So this is going to be a 1 byte long instruction. 1 byte long instructions. MOV A, B is going to be a 1 byte long instruction, and it's going to have this is going to have two machine cycles. One is going to be opcode fetch. Next is going to be memory read. You're going to get the location of the memory from the HL pair, and whatever contents are stored in that memory location, we are going to load A with those data. So this is having two machine cycles. One is opcode fetch and the other is memory read. Next instruction that we see here is arithmetic operation. Add M is similar to ADI data. There we are giving the data itself. The data is going to be located in the next memory location. Here you are going to get the data from memory. How you are going to get the data from memory? You extract the address from HL pair, and at that memory location, whatever data is stored, you are going to add it to A. So A is going to be added with contents of memory, address of which is pointed by HL pair. So this is also going to be a 1 byte long instruction. And it is going to take up two machine cycles, opcode fetch and memory read. So one thing that you can see is all the instructions in indirect addressing mode, they are going to be 1 byte long only, right? Only 1 byte they are going to take up, and they will have two machine cycles, one for opcode fetch and the other for memory read, for reading the memory from the location that is specified by HL pair. So this is going to be common. I don't think we need to write it again and again. We can just look at the instructions. So next instruction is going to be ADCM. What is this going to do? Add the contents of accumulator with the contents of memory along with carry. Okay, again 1 byte and opcode fetch and memory read, two machine cycles. Next instruction is going to be subtract memory, which is contents of memory going to be subtracted from the accumulator. Okay, in every case, okay, memory location is going to be pointed by HL pair. I'm not writing it again and again. I think you understand that. This will be SUBM. Next would be SBB, subtract with borrow. Subtract with borrow. Fine. Next instruction would be CMPM, compare memory, which will compare the data from memory. Okay, we've already seen how compare this instruction is working. This is going to subtract the contents of memory from accumulator, and according to the status of zero flag and carry flag, we're going to judge that which one is greater. Then we have logical operations, which are ANAM. Here A is going to be AND with memory. Then we have ORAM. Contents are going to be OR. And next we have XRAM. Fine, so these are all the instructions that we are having: add M, ADCM, subtract M, subtract with borrow, compare, AND, OR, XOR. All these are going to be 1 byte long instructions and having 2 machine cycles, opcode fetch and memory read. Then we have some instructions for memory writing. Okay, memory write. Right now we didn't see any instruction for 8-bit memory writing. So we have one instruction, MOV M, R. R. This R is register. This can be any register. A, B, C, D, E. Whichever register you want, you can take here. H, L, any register that you want, you can take here. So what is going to happen is, memory is going to be written with contents of specified register. Okay, whatever the contents of this register are, they are going to be stored in the memory. What address? Address pointed by HL pair. HL pair is going to point an address, and whatever address this HL pair is pointing, we are going to store our contents at that address. This is how you can write memory. This is a memory writing instruction. So this is also 1 byte long, 1 byte, and having 2 machine cycles, opcode fetch and memory write. Fine. So these are the instructions we are having. Then we have one more instruction in indirect addressing mode, which is INRM. So what happens here is, in INR operation, what is going to happen is, contents of memory are going to increase by 1. Contents of memory are going to be increased by 1. Suppose HL pair was holding a value 4002. Okay, fine. So what happens after execution of this instruction is, you reach the memory at this location 4002. Some data, suppose 35 was stored. When you execute this instruction, this data is going to be overwritten. It's going to be increased by 1, which makes this 36. So after execution of this instruction, 36 will be stored at memory location 4002. This is how this is working. This is a 1 byte long instruction and is having 3 machine cycles, which are opcode fetch, memory read and memory write. We are performing memory read and memory write both in this instruction. So we are having 3 machine cycles, opcode fetch, memory read and memory write. Fine. Similarly, we are having an operation to decrease the value, which is DCRM. Everything is same, just the contents of that memory location are going to be decreased by 1. Then we have So that is all in indirect addressing mode. Now we are going to look at register addressing. Register addressing instructions. So what happens in register addressing is, you're going to give the instructions, your data, your operand, both the registers are going to lie in the microprocessor itself, so they're not going to take up a lot of memory, okay, because every operand, every data is lying in the microprocessor itself. You just need to perform some arithmetic operations or loading, deloading operations inside the microprocessor only. Suppose, just look at the first instruction, MOV A, B. MOV A, B. So this is the destination register. This is the source register. So data of A is going to change and it is going to be loaded with data of B. Copying takes place, okay. The data from source register B is going to be copied to the destination register A, okay. So the contents of B are going to be loaded in accumulator A. So this is going to be a 1 byte long instruction, 1 byte, and going to take 4 T states only, because only one machine cycles of opcode fetch. One machine cycle of opcode fetch is going to take place. In 4 T states, the contents of B are going to be copied to accumulator A. Next arithmetic operation that we can see is add B. So what happens is, accumulator is going to be added with contents of B. Any other register also, okay. So better to write R here. Any general register, B, C, D, E, H, L, whatever you are giving in instruction, it's going to add, okay. This is going to be any register. So this is also a 1 byte long instruction, and only opcode fetch is going to take. Fine. Okay, and also we know that flags are going to be affected for every arithmetic operation. So according to the arithmetic operation that you're performing, flags are going to change. Next instruction is ADCR, which is add along with carry. So here we're just taking in consideration the carry flag also, okay. Add with carry. Next instruction that we look is SUBR. So here subtraction is going to take place. Same 1 byte. Only opcode fetch, so 4 T states. Next is subtract with borrow, which is SBBR. Here we're just going to take in account borrow also. It's going to be 1 byte, code fetch, 4 T states, right? Then we have logical operations, which are ANAR. Here contents of A are going to be AND with contents of the register, 1 byte, only opcode fetch, 4 T states. Then we have OR AR, where contents of A are going to be ORed with the register, 1 byte, opcode fetch, 4 T states. And then we have XOR operation, XOR AR is going to be XOR with the contents of R, 1 byte, and opcode fetch is going to take up 4 T states. Fine. So similar to the instructions we have seen in indirect addressing mode, there are several instructions to increase and decrease registers, one of which is INRR. INRR, what it is going to do, it is just going to increase the contents of this register with 1 by 1. So this is also a 1 byte long instruction and having 4 T states. Similar to INR, we are having an instruction DCR, which is going to decrease the contents of this register with 1. 40 states. And another instruction that we are having is CMPR. Operation of CMP is same. It's just going to compare the data of the given register with the accumulator, and based on 0 flag and carry flag you can judge. Fine. So these are all the instructions on register addressing mode. Now we have one more addressing mode, which is implicit addressing mode. So what happens in implicit addressing mode is we are not performing any operation on data or operands. We are just performing some operation on several flags maybe or contents of accumulator. Just going to see some instructions. So now we are going to look at some instructions from implicit addressing mode. Implicit addressing mode. So first instruction that we are going to look at is CMA, which is complement accumulator. Complement accumulator. So this is going to perform one's complement. One thing that is worth noting here is no flags are affected. No flags are affected in this instruction. Okay, only contents of the accumulator are going to change. Suppose initially A was having FF. You perform this instruction CMA. So now he is going to have 0, 0, just the contents of the accumulator are going to be complemented. No other flags are going to be affected, right? Okay, fine. So this is an implicit addressing mode instruction. It is going to have 1 byte memory it's going to take, and only 1 machine cycle opcode fetch, 40 states. Fine. Next instruction that we are looking here is STC. STC, what is this going to do is set carry. Set carry means after execution of this instruction, carry flag is going to become 1. Carry flag is going to be 1. Remaining flags are not affected. Remaining flags are unaffected. No other flag is going to be affected. Only carry flag is going to be set. Again 1 byte and 40 states. Next instruction is CMC. CMC is complement carry. Complement carry. So which means if carry flag was 0 initially, you perform CMC, this is going to become 1. And if this was 1, you perform this instruction, it's going to become 0. So whatever was the status of the carry flag initially, you just perform this instruction, it will be complemented. Fine, again 1 byte and 40 states. So this is very obvious. I'm not writing it again and again. Okay, so we are having several instructions to rotate the contents of the accumulator. Rotate the contents means we can shift right or shift left the contents of accumulator. So we know that accumulator is basically a 8-bit register. It is having 8 bits. So by performing shift right or shift left operations, we can just rotate the contents of accumulator. So we are having 4 options for them, 4 instructions. We are going to look them one by one. All of them count in implicit addressing modes only. So we're going to look at rotate instructions. Rotate instructions. There are 4 instructions basically. First instruction that we are going to look at is RRC. RRC, which is rotate right without carry. Rotate right without carry. So what is going to happen in this instruction is basically, suppose initially the contents of accumulator were this was the content of accumulator initially. After we execute RRC, RRC, which means rotate the contents towards right without carry. Without carry means whether the carry flag is 0 or 1, it does not affect this operation. Carry flag, status of carry flag is don't care for us. Okay, so when we are going to rotate the contents of accumulator towards right, this LSB is going to become the MSB, and every other bit is going to shift right by one place. So what is going to be the new contents of accumulator? Fine. So this is how RRC is going to work. So this is a 1 byte instruction and also having only one machine cycle of opcode fetch constituting of 4 T states. So basically what RRC is doing is this is performing a divide by 2 operation. Since every number comes down by 1, every number shifts in its place value by 1, this is performing a divide by 2 operation. Fine. Similar to this, we are having a left shift operation, RLC, which is rotate left without carry. So what is this going to do is, it is just going to rotate the contents of the accumulator to the left by 1 bit without any effect of carry flag, right? This is also a 1 byte instruction and having one machine cycle of opcode fetch of 4 T states. So basically this is performing a multiply by 2 operation, because we are shifting every bit to left by 1 place. That is why we can say that this is performing a multiply by 2 operation. Other than these 2 instructions, we are having some instructions which are using the carry flag, which are making use of carry flag. So there is an instruction RAR, which means rotate accumulator right. So what happens in this instruction is, in this instruction also contents of the accumulator are going to shift by 1 bit towards the right, but here LSB is going to be the carry flag. Right? So what happens here is, let us look at an example. Suppose 0 0 1 0 1 0 1 1. These were the contents of the accumulator and carry flag was 0. So after execution of RAR, every bit of this accumulator is going to shift right, and this carry flag is going to be the MSB. This is going to come in place of MSB, and this carry flag will be overwritten with the LSB. So finally we are going to have this is what you're going to have after the execution of this instruction, right? So here we are also using the carry flag. Fine. So this is also a 1 byte instruction and having 4 T states. Similar to this, to shift left the contents of accumulator using the carry flag, we are having an instruction RAL, which is rotate accumulator left with carry. This is also 1 byte long instruction. Fine. So these are some instructions that we are having for rotation of accumulator, rotating the contents of the accumulator.